Okay, good morning. Today is Monday, June 7th. So this is the final lecture meeting for the semester. So congratulations, you're almost there. Some of you have actually taken the final exam and are already done with the course. So that's cool. I did push back the final date for the third and final exam chapters 1 through 3. And so you still have, I think, a week to do it. So you still have a lot of time. So good luck with everything. Good luck with all your classes. So what I'm going to do today is I'm going to talk about the final section of chapter 3, which is limiting reactants. Okay, so let me go over that. Let me start on that. So the idea here is that imagine that you're making something in a factory. So imagine that you need two different things to make a finished product. So, you know, whatever analogy you want to use, it could be, you know, if you want to use Twinkies as an example, Twinkies have like the bread on the outside and the filling on the inside, two different things, which I guess would be like cake batter and frosting, right? It could be sandwiches. It could be like two pieces of bread and a piece of cheese on the inside, or a cucumber. It could be something else. It could be like some sort of, I don't know, like an iPhone and an iPhone case, two things getting put together. Whatever analogy you want to use. Imagine you're making something. The idea is that you're going to have at least, you know, two different things, typically. So you might have like, you know, item 1 and item 2. And then those two are going to go into some sort of process where they're combined, right? They get combined into a final product. So this is your finished product, right? So in chemistry, that's essentially what we do. We put in reactants and we get a product out. So this is really a reactant. And this is a reactant, right? So even if we don't know anything about the structure of an atom, how many protons it has, what the electrons are doing, even if we don't know anything about that, we do know that in a chemical reaction, we put in something and we get something out, right? And what we put in is the reactants. Sometimes it takes more than one. Sometimes it takes 2 or 3 or 4 reactants. And then we get some products out. And we might get more than one, right? We might get 2 finished products out. So here's your finished product here. Right, so you might get 2. You could even get 3 or 4. So an explosion, for example, usually produces quite a few. If you take something like nitroglycerin, you get like 4 products out of it, at least 4. And those are just the main products. There's other ones as well. So in any case, input, output, right? So, you know, sometimes we're interested in how this happens, but we're not dealing with that in this course. That's a more advanced topic. We're just interested in how much goes in, how much comes out. If I put this in, how much do I get out, right? In a sense, it's an economic issue. Okay, so let's take a look at an example. So the idea of limiting reactants is that one of these reactants is going to limit how much of the products you can get out. And we call that the limiting reactant. So let me show you an example, okay? So it says in this example that you have nitrogen. Nitrogen is N2. Remember, there's 7 diatomics. The diatomics were H2, N2, O2, F2, and then Cl2, Br2, and I2. Those are your diatomics. So if they say that nitrogen reacts or nitrogen is produced, you're going to use N2, okay? So nitrogen gas reacts with hydrogen gas. Okay, remember hydrogen is H2 also, to form ammonia. Now there are really 3 substances that you should just know their formulas for. One is water, H2O. Ammonia is the second one, NH3. And probably the third one is carbon dioxide, CO2. Although back in chapter 1, we learned how to name, or chapter 2, I think it was 1. No, it's 2. We learned how to name compounds, right? So carbon dioxide, we could figure out that's CO2. But those 3 substances are so common, we should know what they are. So then in the question it says, so there's your reaction. Suppose 7 moles of N2 and 1 mole of H2 are mixed. Okay? The question is, 1, could half, 1/2, right? So I'm going to write this in parentheses, 1/2 the N2 react? And if yes, how many moles of N2 would be produced? Okay, so I'm going to actually say this is sort of an odd question. This first part is kind of an odd question, but it is something that they put into ALEKS, so I want to go over it. So let me show you how to approach this. It's a long word problem, and you have a lot of steps here. You may have noticed these problems are getting more challenging, right? They're becoming more difficult. And so that's sort of a prelude to the next course. Okay, so the first step is you write the balanced equation. So what it tells us is that N2 is a gas, and it's reacting with H2. Actually, I didn't write in here, but it's a gas. I was just trying to save a little time. And then it tells you ammonia gas. So that would also be a gas. All right, it tells you it's a gas. The balanced equation is key to this. You have to balance the equation or you're not going to get the right calculation. So I'm going to do the nitrogen first. There's 2 over here, but there's only 1 over there. So I'll put a 2. Now we've got 6 hydrogens there. So I put a 3 over there, right? 3 times 2 is equal to 2 times 3. Now you got your balanced equation. That's your starting point. You balance the equation. So now, could half of the nitrogen react? So here's what you do. Okay. I'm going to erase this over here. I'm going to write down the numbers that they gave us. I think that's a good way to do it. Just write down 7 moles so that you have it right next to the equation. And 1 mole, it said, right? 1 mole. Okay. Now I can erase this. Okay, so the question is, could half of the N2 react? So here's what you're going to do. Here's your strategy. Calculate the moles of NH3 produced from each reactant. Okay, so each reactant. So there's going to be 2 calculations. That's the key to this. Okay, so here's what I'm going to do. I'm going to show you how we do this. You take the first one, which is 7 moles, and write it this way, 7 moles of N2, right? Now, the balanced equation, we talked about this in the previous lecture in section 3.6. So if you're really still struggling on that, go back and rewatch that lecture. You're going to use the balanced equation. So you're going to multiply that by 2 moles of NH3 divided by 1 mole of N2. I'm using the coefficients just like we talked about in chapter 3.6. Okay, well, what do you get? You get 14, right? So that tells us that if all 7.0 moles of nitrogen react, we will get 14.0 moles of NH3. Okay, that's what that tells us. However, this is a limiting reactant problem. You can recognize limiting reactant when you're given the amounts of both reactants. That's how this differs. Now we do exactly the same calculation, but with H2 instead of NH3, right? As I said, from each reactant. So we're given 1 mole of H2. And again, now it's 2/3, right? Now it's 2 moles of NH3 per 3 moles of H2. So look what happens. Now you get 0.67. Actually, they say to round it to the nearest tenth. So I'll write it as 0.7. Okay? So what has happened is, even though we have enough N2 to make 14 moles of NH3, we don't have enough H2 to make that amount. In fact, we only have enough H2 to make 0.7 moles of NH3. So what we would do is we would call this the limiting reactant. The limiting reactant is the reactant that produces less of the product. So H2 is the limiting reactant. The other reactant, the one that gives you more, is called the excess reactant. So actually, let me write it up here. Limiting reactant, excess reactant. And then this is the product, right? So we would claim that N2 is the excess reactant because it can make a lot more ammonia, NH3, than the hydrogen can. The hydrogen is the limiting reactant. It limits how much of the product you can get. Again, analogies. If I had 3 slices of cheese, but I had 5 loaves of bread, you could make a lot more sandwiches, right? A loaf of bread might have 20 slices in it. So you can make a lot of sandwiches. But if I only have 3 slices of cheese, I'm limited, right? Can't make that much. So the cheese would be a limiting reactant and the bread would be the excess reactant in that particular case, right? So we haven't answered part 2. Actually, we haven't even answered part 1. So part 1 says, could half of the NH of the N2 react? Okay, well, this 14 moles of NH3 is what you would get if all 7 moles of this reacted. So what would be half of that? What would be half of 7 moles, right? It says half of the N2. Half of the N2 would be half of 7 moles. That would be 3.5 moles, right? So now, how much ammonia would you get? Well, 3.5 moles of N2, just like we did here. 2 moles of NH3 per 1 mole of N2. You're still going to get a lot. You're still going to get 7 moles of NH3. That is still a lot more than 0.7 moles. Yeah, make sure your powers of 10 are right here, right? 7 is 10 times as much as 0.7. So the answer is no, not a half. In fact, it's really 0.05. It's really 5% of it would match it up pretty good, right? But the point is that the answer is no, because even with half as much N2, that's half as much as we really were given, we still would have a lot more ammonia than we would have based on the hydrogen. The hydrogen would run out before you could even make 0.8 moles of NH3, right? Think about it. If you've only got 3 slices of cheese, you can't make 25 sandwiches. You can't make half of that. You can't make 12 sandwiches because you only got 3 slices of cheese. So the maximum amount of ammonia we could make is right here, 0.7, okay? Now it says, if yes, how many moles of N2 would be produced, of NH3, I'm sorry, NH3. That's what's produced. If yet, well, the answer is no, right? So we could say no and then say really only 0.7 moles of NH3 is going to be produced. That would be true. But it says if yes. So since the answer is no, I guess we wouldn't answer part B. So in a way, that's why I think this is kind of a strange problem, because either way, we can calculate how much ammonia. Okay, so let's take a look at another example. Okay, here we've got 2 reactants and 2 products. So it says that methane gas, and just to save time, I'm going to write down the formulas. So it says methane gas reacts with oxygen gas to form carbon dioxide gas and liquid water, so H2O liquid, okay? And then they say we mix 11 moles of CH4 with 3 moles of O2. And then again, it's really the same question. Can 1/2 of the CH4 react? Okay, and then the question then says, if yes, calculate the moles of CO2 produced. Okay, pretty straightforward. Again, you can't do these problems unless the equation is balanced. So let's balance it. There's 1 carbon on each side, so that's balanced. There's 4 hydrogens, but there's only 2 there, so I put a 2 to make that 4. And now you've got 2 oxygens plus another 2 oxygens, so that's 4. So you put a 2 here, 2 times 2 is 4. Now it's balanced. So here's a slightly varied way to solve this. Instead of actually calculating 11 moles of CH4, let's do the half. Let's go directly to half. So 1/2 of 11 moles. That's what it says. Can 1/2 of it. So that'd be 5.5 moles. Okay, now we do what I said, which is calculate the moles of CO2 from each reactant. Okay, so let's do the CH4 first. 5.5 moles of CH4. And we want carbon dioxide. That's over here. That's a 1, and that's a 1. So 1 mole CO2 for every 1 mole CH4. So you get 5.5. Okay, so a half of what we put in, because the question was, can a half of it react? That's how much CO2 we would get. That would be our answer if CH4 is the limiting reactant. The limiting reactant tells you how much of the product you're going to get. But now we have to figure out based on the O2. Let's do this one. So for this one, we have 3 moles. And like I said, it's probably a good idea to put your moles up here just so that you can have them handy. So let's try the second one. 3 moles of O2. And now the relationship is 1 to 2. See those coefficients? That's why we balance equations, really, is so that we can do this calculation. Okay, so you get 1.5. Okay, right? Half of 3. So look what happens. This is still smaller. This is a smaller number. So that means the O2 is the limiting reactant. Right? So this is the amount produced. Okay? So that would mean that O2 is the limiting reactant. CH4 is the excess reactant. Even if we're only using half of it, it's still the excess reactant. So the amount made would be 1.5. And the answer then is no. Not even half of it can react because we have so little O2. The amount of CH4 that can react is limited by the amount of O2 that we have here. And so then the question is, how many moles of CO2 would be produced if yes? Again, the answer is no, so we wouldn't really likely answer that, but we could because our answer is right here. The limiting reactant tells us how much. The smaller of these two. You want to pick the smaller one. Okay. Again, come back to the sandwiches, right? If you have 1 slice of cheese, let's do it the other way. Suppose you have 20 slices of cheeses, but you only have 2 slices of bread. You only make 1 sandwich because you got 2 slices of bread. You got a lot of cheese, but it's not enough. I mean, it's too much. You really only have 2 slices of bread. So the limiting reactant is what you're looking for. Okay. Cool problem. All right, let's take a look at another one. Different type of problem here. This one is going to go in through a lot of steps, so you may need to watch this video a couple times. You may need to practice it quite a bit to get it. So this is a limiting reactant problem. So they tell you that gaseous ethane. So I'm going to write this straight to the equation because, again, it takes a long time to write all this down. So I'm just going to go ahead and write it as an equation. Gaseous ethane is going to react with gaseous oxygen. Right? So there's our reactants. To produce gaseous carbon dioxide and gaseous water. Okay? Then it gets to the numbers, right? So the thing that's really challenging about these limiting reactant problems is you got to write a whole balanced equation from the words and then do the calculation. So if you can do this calculation, you're well set up for the next course. Okay, so let's take a look. Suppose 23.8 grams of ethane is mixed with 23 grams of oxygen. And then the question is, calculate the minimum mass of ethane left over by the reaction. Okay, now what I'll say of this is they're actually giving you a hint. When they say that ethane is left over is telling you it's the excess reactant. That's what that means. It means that you're gonna have some left over, right? So if I had 2 slices of cheese, but 25 slices of bread, you're gonna have bread left over. So it's the excess reactant. Same thing here. They're telling us that it's the excess reactant, which means oxygen is the limiting reactant, okay? Right, one's gonna be excess, one's gonna be limiting. So step 1, balance the equation. This one is a little trickier to balance. You got 2 carbons here, so you need 2 carbons on the right. You've got 6 hydrogens on the left, so you need a 3 here to make it 6 on the right. And then you got to do the oxygen. You're going to get a fraction, right? 2 times 2 is 4. 3 times 1 is 3, so you got 7 oxygens. So 7 halves, right? What you do is you say, look, this is 2. So you just take the number you get over here and divide it by 2. Because 7 halves times 2 is 7. If you want to, you can do the next step, which is to multiply everything by 2. It's unnecessary, but you can do that. So multiply everything by 2. And there you go. Okay, so there's your balance equation. Now, here's how you approach it. This is my recommendation. Step 1, convert mass to moles. Step 2, calculate moles of desired product. Okay. Step 3, convert moles of product to mass of product. And then do this for each reactant. Now, one of the things that makes this a little difficult is that they've really given you probably the most difficult, I would claim this is the most difficult limiting reactant problem you can do, because they don't even tell you anything about the product. They don't care about the product. They just want to know something about the reactant. So what I would suggest is just, if they don't tell you anything about the product, pick one of them. Just pick one of the products. It doesn't matter which one. So I'm going to pick CO2. Okay. Now, let's go through it. This is going to take up some space here, but I hope I can fit it in here. So we're going to start with the first reactant. Convert to moles. Take the moles of that reactant, convert it to moles of product, and then convert moles of the product to the mass of the product. Some of these numbers, we're not going to need them in our answer, but I want to go through the full calculation so you can see how to go about this. So let's start with the first reactant. 23.8 grams of C2H6. You got to calculate the molar mass, right? You convert mass to moles by dividing by the molar mass. So 1 mole of C2H6 per 30.08 grams. Where did I get that 30.08 grams? That's the molar mass. I calculated it. 2 carbons, 6 hydrogens. That's back in section 3.4. If you don't know how to do that, you got to go back and review that, okay? So now we're going to divide it by the molar mass. So 23.8 divided by 30.08 is 0.791 moles of C2H6. Step 2, now figure out the moles of one of the products. So if they said carbon dioxide, you could use that. But if they don't, use any one you want. So I'm going to use the CO2. So 791 moles of ethane times 2 divided by 1. 2 moles of CO2 per 1 mole C2H6. So that's going to give you twice as much, so times 2. 1.58 moles. Now it's carbon dioxide, right? That's the section 3.6. Then convert it to grams. 1.58 grams of CO2. The molar mass of CO2 is 44.01, right? 1 carbon, 2 oxygens, that adds up to 44.01. So times 44.01, okay? So what do you get? You get 69.6 grams of CO2. Now, I'm going to write this down over here. Okay? And then that's from C2H6. If all of the C2H6 reacted, that's how many grams of CO2 would be produced. It actually, what we know is that it actually, that amount didn't react. So now let's go back. Oh, actually, you know what? I'm going to erase this. I want you to be able to see the problem. Okay. So now let's do the second reactant. 23 grams of O2, divide by the molar mass. So 1 mole of O2, 32 grams. Right? That's the molar mass of O2. So a little less than a mole. So 23 over 32 is 0.719 moles of O2. Again, let's pick CO2. So it's 2 moles of CO2. I'm sorry, let's use this one over here. It's 4 to 7. So 0.719 moles of O2 times 4.7. 4 moles of CO2 per 7 moles of O2. By the way, it doesn't matter which of these we use. We could use this one or we could use this one. The ratios are the same. 7 to 2 is the same as 7 halves to 1, or 7 halves to 4. I'm sorry, 7 to 4 is the same as 7 halves to 2. So it's the same ratio. So either one. So actually for the first calculation, I think I used this balanced equation. For this one, I'm using this one, but it doesn't matter. It's the same. 0.719 times 4 over 7. And yeah, it's 0.411 moles of CO2. And then again, convert it to grams. So it's 44.01 grams of CO2 per mole. So that's 18.1 grams of CO2. So now I'm going to write this down over here. 18.1 grams of CO2 from the O2. So let's go through this real quick. Which one is actually going to be produced? The smaller amount. Again, go back to your sandwiches. If you only have a slice of cheese, you can't make 25 sandwiches. It's the smaller amount. So what that means is this is the amount actually produced, 18.1 grams. That means this one here is the limiting reactant. This one is the excess. So this is excess, but we knew that, right? It actually told us. It told us that the ethane was going to be in excess, and it told, by default, that's telling us the oxygen is limiting, okay? So if the question was how much CO2 would be produced, you would have your answer 18.1 grams of CO2. That's a very standard type of problem. This one goes to the next level though. It says how much ethane is going to be left over after this occurs, okay? So let me show you how to do that. Well, I'm not going to save that. I'm just going to delete, I'm just going to erase this. So let's get back to the question. The question says how much C2H6 is going to be remaining. That's called the excess amount, okay? All right, so here's what I'm going to do. I'm going to come back and say this is the limiting reactant right here, 23 grams, okay? 23 grams of O2 reacted. Because that's the issue, right? A limiting reactant, all of it reacts. So really what you have to do then is just say if 23 grams of O2 reacts, how many grams of C2H6 would have reacted? We can't use the 69.6 because that would be if all of it reacted, but it didn't all react. So we can't even use that number. All we can do is start with this number and this number. So let me show you how to do this. You say, okay, how many moles is this? Well, 1 mole of O2 is 32 grams. Okay, put that in parentheses. So 23, we already did this, but I have to write it again because I erased it. Okay, this is how much reacted. That's how many moles. Okay, well, now let's figure out how many moles of C2H6 this is. Okay, it's, oh, let's use this balanced equation down here because a lot of people don't like fractions. So we'll use this one down here. 2 moles reacts for every 7 moles. So 0.719 moles of O2 times 2 moles of C2H6 for every 7 moles of O2. Okay? 2 sevens, right? Every time 7 of these react, 2 of those react. So multiply that by 2 sevens. You get 0.205 moles of C2H6. Okay? That's how many moles of C2H6 react. Isn't that easy? In order to figure out how much of the excess reactant reacted, all you got to do is figure out how many moles of the limiting reactant you have and use the coefficients to figure out the moles of the excess reactant that reacted. Okay? That's kind of cool. So now let's convert that to grams. 0.205 moles of C2H6 times, now how much did we say this weighed? We already did that, 30.08. That's the molar mass. Remember, divide by molar mass to get moles, multiply by molar mass to get grams. So 0.205 times 30.08, and you get 6.18 grams. That's kind of cool. 6.18. So now we know how much reacted, 6.18 grams. We also know how many grams we started with. So actually now we can calculate this. How much is going to be left over? So be careful when you do this step. It's easy, but you have to get the concept. Suppose I start off with 23.8 grams. That's how much it started off with. How much reacted? 6.18 grams. So if you subtracted 6.18, the amount that reacted, what you get is the amount that was left over, right? If I took 8 slices of cheese and I reacted 3 slices of cheese, I would have 5 slices left. So to figure out the amount remaining, you just take the difference. The amount that you started off with in grams minus the amount that was reacted in grams, and that will give you the number of grams left over. So 23.8 minus 6.18, and they say to round it to a tenth, I think. So 17.6 grams of ethane left over. Okay, so I actually went through 2 complete calculations there. The first one was to show you how to get the amount of products from the limiting reactant. The second one was more to this question, how much of the excess reactant, the C2H6, is left over. So that's really 2 separate problems, but I wanted to show both of them to you because those are essentially the 2 types of limiting reactants that people get asked. Okay. Let's see. Okay, let me come back over here. And let's go on now to something called the percent yield, because you have to do percent yield as well. Again, still in section 3.7. So they tell you that you have compound A. And it's going to react with compound B. Okay. And you're going to get one product. So it tells you that these are the reactants. Okay. And they tell you that the usual percent yield is, I'm sorry, of C is 87%. That's the usual percent yield of C. So then it says, suppose 1.5 grams of A reacts with excess B and 6.5 grams of C are successfully isolated. So they're using a lot of words here that they don't need to because they're just trying to give you advanced language. Successfully isolated means products. That's how much you produced. Okay, so there's all your information, right? So now, question A. Find the theoretical yield of C. There's your first one. Then, how, so this is question A. Question B is how much B was consumed, used in the reaction. Okay, question mark. So what is the theoretical yield of C? And then how much B was consumed in the reaction, okay? So let's take a look at this one. What I want to do is I want to give you the formula for percent yield, okay? So percent yield, I'm going to write it this way. Percent yield is the actual yield divided by the theoretical yield times 100%. That's the definition of the percent yield, okay? The percent yield is essentially a measure of how close to the ideal amount of product did you get. So for example, suppose I have a factory and I'm making sandwiches and I have 20 slices of bread and 10 slices of cheese. And I want to do a sandwich with 2 slices of bread and 1 slice of cheese, 2 to 1, right? I have 20 slices of bread. How many sandwiches could you make? That would be your theoretical yield. In theory, we could make this many sandwiches from 20 slices of bread. It'd be 10, right? You could make 10 sandwiches from 20 slices of bread. That's called the theoretical yield. So if I put in 5 grams of salicylic acid and 2 grams of phosphoric acid and 1 gram of acetic anhydride, how many grams of aspirin, acetylsalicylic acid, I'm going to get? You do the calculation based on the amounts you put in, and that's called the theoretical yield. Based on putting this many grams in, the theoretical yield would be 6 grams. You know, that's the theoretical yield. Okay? The actual yield is how much do you actually get. So if you actually go through and weigh it, how much do you get? You almost always get, in fact, you always get less than you theoretically can get because there are always impurities. Nothing is 100% pure. So the amount of reactant you're putting in is actually different than you think because there's impurities. That's one issue. Another issue is that you can't actually collect it all and move it onto another container without losing some. Think about if you're making cake batter. when you make the cake, some of that batter, no matter how well you scrape it out, is going to be left in that bowl and it doesn't go into the cake. That might be a very small amount, and that can be a small amount. There are other reasons as well. Sometimes reactions do not produce only one product. They're making the product you want, but they're also making other things that you can't stop from happening. So some other things get produced, so it's not your product. So the theoretical yield, the amount that you calculate you would get, is always more than the actual yield, the amount you actually get. Okay? So let's take a look at this. In a sense, they're giving us a lot. Really what they're doing is they're saying A is reacting with B to give us C, right? Here's your reactants, here's your product. Reactants, product. Okay. The usual percent yield is 87%. So they're telling you this right here is 87%. Then they're saying, hey, 1.5 grams reacts with excess B and 6.5 grams of C of the product are successfully isolated in the reaction. Got someone in here. Okay. Oops. Sorry, hold on 1 second. There we go. Okay. So now based on that, they want us to find the theoretical. So they want us to get this. Okay. So all you really got to do is you just got to figure out what the actual yield is. We know the percent yield. So if they want the theoretical yield, you just need the actual yield, right? You need these two to get this third one. So what's the actual yield? Well, they tell you right here. The amount of C that's produced is 6.5 grams. That's the actual yield right there. Okay, so let's go through it. I'm going to erase this here. This is just an algebra problem. So we're told 87% is equal to the actual yield, which is 6.5 grams, divided by the theoretical yield. So I'm just going to put THY for theoretical yield. There's no reason to spell that whole thing out. Times 100%. Okay? And they're asking us for the theoretical yield. Okay? Well, let's do the algebra. We want this thing that's all the way down at the bottom in the denominator, right? So you multiply both sides by the theoretical yield, and that's going to give you 6.5 grams. I'm putting parentheses in here just so you can sort of see what we got, right? So I multiplied both sides by theoretical yield. By multiplying the right side by theoretical yield, you cancel it. Then we want to isolate the theoretical yield, so you divide both sides by 87%. So that'll give you theoretical yield is 6.5 grams times 100% divided by 87%. Okay? So let's see what you get. 6.5. Let me just make sure this is clear. 6.5 times 100 over 87, and you get 7.47. I'm going to round it to the nearest tenth, 7.5 grams. So that's your theoretical yield. So notice the actual yield and the theoretical yield are both in grams. So here's our sort of conclusion from that. Actually, I don't want to erase anything because we still have part B. So here's a little table. Actual yield, 6.5 grams. Theoretical yield, 7.5 grams. Percent yield, 87. Okay? So really all we're saying is that 6.5 grams is 87% of 7.5 grams. So just go back to this formula. When you do these kinds of problems, they're going to give you two of them. You just have to figure out which two they gave you. In this one, they gave you the percent yield and they gave you the actual yield. You're going to calculate the theoretical yield. Okay? Now, the question is, and this is an interesting one. This is unusual. Most textbooks don't ask this question. This is an ALEKS-specific type of problem. So you won't find this one in your textbook. How much B was consumed by the reaction? Okay, how much B got consumed? Well, we have some information here. They told us in this problem that when 1.5 grams of A reacts, 6.5 grams of C are produced, right? So that was one piece of information that we got there, and that this is 87% yield. Okay. So now let's go back and take a look at this. What we know is that the mass of C produced equals 6.5 grams, right? So 6.5 grams has got to be equal to the mass of A that reacted plus the mass of B that reacted. Okay, let me actually erase this down here. Okay. So how much of A reacted? Well, we know 1.5 grams of A reacted, right? So 6.5 grams, which is C, is equal to 1.5? Yeah, 1.5 grams of A plus the mass of B. Okay. So what's the mass of B? Well, the mass of B would just be the difference. It would be 6.5 grams of C minus 1.5 grams of A. And so that would be 5.0 of B reactant. Okay. Or consumed. They use the word consumed. Okay. So that one right there is just based on just looking at, in particular, this problem, what they did was they set it up that there's 2 reactants and only 1 product. So if you know the amount of this that's produced and you know the amount of this that would be reacted, you can calculate the amount of this that must have reacted. These 2 masses has got to equal the mass of the product. So that's where that one comes from. Okay. Let's see. Okay. Another theoretical type question is they tell you in this one, you've got aqueous hydrobromic acid. They give you the formula, HBr. They tell you it's aqueous. Remember, aqueous means dissolved in water. And that is going to react with solid sodium hydroxide. Okay, solid sodium hydroxide. That's going to produce aqueous sodium bromide. The nice thing about this one is they give you all the formulas. So you can write the formulas down, and liquid water. Okay, so you don't have to figure out the formulas. Now, here's what they tell you. You've got 59.9 grams of this. And it's going to react with 23.4 grams of this. Okay? And then they ask you to calculate the theoretical yield. Let me just make sure I get the wording right, of NABR. Okay? Theoretical yield. So just a reminder, remember we had 3 things. We had percent yield. This one's just going to be a percent. That is equal to the actual yield. This is going to be a mass in grams. And that's divided by the theoretical yield. I'm going to abbreviate it. This is also a mass in grams times 100%. So just be careful when you do these problems. The actual and theoretical yield are both masses. They're not percentages. The percent yield is a percentage, okay? So it's a mass divided by a mass times 100. That's what converts it to percent, okay? So let's go through this one. Now, this one's a little tricky because the molar masses, but let's go through it. the theoretical yield. That means we're going to find the mass of this. Okay. This is really just a limiting reactant problem. I know they put it under theoretical yield, but it's really theoretical yield is limiting reactant. How much of the product you're going to get. So let's go through it. It's the same problem we just did at the beginning. You take the mass of what you start with, convert it to moles, find the moles of your product. Let's make sure everything's balanced. It looks like there's 2 hydrogens on the left and 2 on the right, 1 bromine on either side, and 1 sodium on either side, and 1 oxygen. So it's already balanced. We're good there. So let's start with the first one. 59.9 grams of HBr. Okay? So we got to divide that by the molar mass. Okay? Bromine and hydrogen, that would be 80.91 grams. Again, that's the molar mass. Okay, so 59.9 divided by 80.91. 0.740. We're interested in sodium bromide. It's one of these for every one of those. So 0.74 moles of HBr times 1 mole of this for 1 mole of that. So you get 0.74. Because everything's 1 in the balanced equation, you're going to get 1. Okay. Now you got to convert this to mass. So 0.741 moles of NABR. Now, how much does NABR weigh? It's 22.99 for the sodium, plus 79.9 for the bromine, so that's 102.89. Okay, so yeah, being able to do these molar mass calculations, you got to do them quickly because that's just a tiny, tiny bit of this calculation. Everything that we've learned in chapter 3 is in this problem, balancing the equation, mass to mole conversion, mole to mass conversion, theoretical calculation, theoretical yield, all of it's in there. So 0.741 times 102.89, 76.2. Okay, so what I'm going to do is I'm going to come over here and write this down. 76.2 grams from the HBr. Okay, so we don't know whether that's the answer yet because it could be that HBr is the excess reactant. The actual amount, the theoretical yield of the product is from the limiting reactant, so we don't know which one's limiting yet. So let's do the other reactant. 23.4 grams of sodium hydroxide. Convert that to moles. 1 mole of sodium hydroxide is, I think it's actually 2333, it's 40.00 grams. So 23.4 over 40. And you get 0.585. Okay. Figure out how many moles of sodium bromide that is. Well, it's going to be the same because it's 1 to 1. So 0.585 moles of NaOH times 1 mole of NaBr over 1 mole of NaOH, right? It's 1 to 1. So 0.585. Okay, I ran out of room here. Okay, so I'm going to have to come up here. So 0.585 moles of NaBr. And then how much did we say NaBr weighed? We had it here, 102.89. Okay, so times 102.89, and you get 60.2. So we have 2 answers. This is from the NaOH. Okay, you pick the smaller one. The theoretical yield is the smaller one. So that means they don't ask you this question. They just ask you what's the theoretical yield? Well, your answer would be there, 60.2 grams. But you also want to be able to talk about it. So here's what we would say. We would say the HBr produces more than that. It has the potential to produce more than that. So it's the excess reactant. And the sodium hydroxide is the limiting reactant, okay? So our theoretical yield would be from the limiting reactant, and that would be 60.2 grams, okay? The excess reactant would be HBr. There's going to be some of it left over, and we went through that calculation earlier, how you could figure out how much of the excess reactant is left over, okay? But it doesn't ask you for that. It just asks you for the theoretical yield, which would be that value there, okay? Now, there's one more problem I want to show you. It's actually pretty simple, but I want to go through it just so that we've covered everything. So that is identifying four types of reactions. So here's the four categories: combination, decomposition, single displacement, and double displacement. Okay, so let me show you in general how to figure this out. It's pretty simple. There are different ways of classifying reactions, and this is one system. You'll learn a different system in Chem 11. You'll learn a system in Chem 12. If you take anatomy and physiology, you'll learn a different physiological system of classifying reactions. If you take general biology, use different systems, okay? This is just for this course. Combination is when you have something that's simple reacting with another thing that's simple to get something more complex. Combination, right? So A plus B turns into AB. AB is more complex than A. AB is more complex than B. That's called a combination. Decomposition is essentially the reverse of that. You've got something that's complex and it breaks up into things that are simpler, right? So CD is more complex than C. It's more complex than D. So if CD turns into C plus D, two different things, that would be decomposition. Generally, combination, you have more reactants, fewer products. Decomposition is the reverse. You have fewer reactants, more products, okay? Meaning more types. Single displacement is where you have something that's usually an element and it reacts with a compound, okay? And that will it will displace, which means changes partners. So you'll get something like AB plus C. So see what happened? This guy, which is single, is displacing the B from the C, right? So the A took the B and now the C is all, that's called single displacement. Double displacement is when you have two compounds and they switch partners. So A will go with C and B will go with D. So now essentially A is displacing A is displacing D and B is displacing C. So they switch partners. So this is double displacement, okay? So let me show you an example. All you have to do with these is just classify them. So here's an example where they say, hey, we want you to classify this. So you have Ca plus F2, and that's going to go to CaF2. Here's another one. H2SO3 goes to H2O plus SO2. And then 2Al plus 3ZnBr2. That's going to go to 2AlBr3 plus 3Zn. Okay. So let's take a look at this one. Okay. So the first one is pretty straightforward. Take a look at it. You've got an element plus an element to form a compound. So you're taking something that's simple. It's reacting with something that's simple. Elements are simple, right? To form something complex, one product, a compound. So that's a combination, right? something simple plus something simple to something complex. So that's combination. Oops, let me write it over here. Combination. Okay. The second one is H2SO3 turns into H2O and SO2. So look at that one. One compound turning into two simpler things, right? Complex to simple. So that's going to be this one right here. That's decomposition. The H2SO3 is like this. The H2O is one of the products and the SO2 is the other. So that's a decomposition. Okay. The third one, if you take a look at that, now you got Al and it's reacting with ZnBr2. So there's an element, right? And there's a compound. Look what happened. Essentially, the aluminum is now with the bromine. The aluminum now is combined with that. So you had something that says element, so like this, A, and it's combining with a compound, so that's like BC, to now form a new compound, AB, plus an element, C. So that's a single displacement right there. Okay, let's take a look at a double displacement. AgNO3 plus NaCl goes to AgCl plus NaNO3. Okay, that's double displacement. Why? You got two parts here, Ag and NO3, so that's like AB. You got two parts here, metal with a nonmetal, NaCl, so that's like plus Cd. And now the silver is now with the chlorine, and the sodium is now with the nitrate. So the sodium is with the nitrate. So there's your double displacement. Okay. So that's actually the last type of problem in this chapter. They just sort of threw this in here in the textbook and in Alex, just to kind of give you the last sort of problem, which is classifying these equations. Okay, so that's a relatively simple one. 3.7 is hard. It's hard work for most people. So you're really going to have to put a lot of time into it if you want to be good at these problems. That's essentially some real chemistry calculations is 3.7. Okay. All right. So limiting reactants. Good. So like I said at the beginning, you still have time to get through this. You have actually, I'm looking at the homework now. The last objective is I changed the date. I originally had it for like 6.4 or 6.5, but I pushed it all the way back to the 16th. Okay, so you have a lot of time to do it, but I would recommend putting a lot of effort into chapter 3. They're challenging problems, but they're good if you can do them. And let me just don't save this. I just want to do a real quick look here at the assignments. So the last exam, which is the final exam, I pushed back that date as well. So the final exam, which is 1 through 3, is, again, it's not due until the 16th. So you still have, I guess that's what, 9 days? So you still have the 16th. I have to get the grades in that day, so that's why it's due that day. It's a little bit longer than the previous exams. It's 25 questions. It's a mix from chapters 1 through 3, okay? All right, good. I also changed the dates on the practice exams because I wanted you to be able to practice, right? So the practice exams, of course, they're not graded, but I wanted you to be able to practice those. So I'm just checking. It looks like I've got them almost to the end there, because some people like to do the practice exams all the way to the end. So let me just make sure they're set up as the 16th, and I think they are. So you should be set. So practice the exams, finish up all of the homework. Looks like everything is pretty much set here for the 16th. And then grades should be in pretty quickly. Now remember, this course, the thing about this course is you don't get a grade for it. You just get a pass or no pass. So you don't have to get, 95% to get an A or anything like that, because there aren't any grades. You're just going to get pass or no pass. But hopefully this will set you up well for Chem 11. And good luck with everything. Reach out to me if you have any questions. Good luck on all your final exams. Good luck on all your final papers if you have that kind of stuff. And if you're taking Chem 11 in the summer, good luck with that. and take care.